it going, everyone? Today we're going to be talking about forensics again. Most images were created with Crayon.com in this presentation, but some were created with Stable Diffusion, which I've been using more recently. So first we'll review a little bit of what we talked about last time about steganography and steg analysis. And then we'll get into a new topic of packet analysis. We'll cover packets, network layers, and using Wireshark. So first, let's review. So steganography. It's the art and science of concealed writing. It's very different from encryption, which doesn't really attempt to hide. It's just like this big blob of random letters and digits. Steganography looks like normal pictures, but there's messages hidden in it regardless. And we looked at the digital form of steganography. Of course, there's many ways to do this. One way is file format, to take advantage of the assumptions that people make about files on their computers. In our lecture, we demonstrated writing past the end of a file and transmitting a secret message that way. Images. There's lots of ways to do steganography with images, but we focused on the least significant bit. So images are made up of pixels, and these pixels have different parts to them, red, green, and blue most of the time. And the significance of the digit of each pixel is how much the color changes when you change that bit of the quantity. We find if we change the least significant bit, you don't really see any difference in the picture at all, so that can be used as a covert channel. And since we don't want to do this by hand, it'd be pretty infeasible, we looked at a tool that can do it for us automatically. In steg analysis, we just briefly touched on this topic because it's really hard. The best advice I can give is to look at tools. Such as steg detect, and this list of tools can be helpful as well. But knowing what steganography method was used is very helpful. Knowing the cover image before the message was added is very helpful. And hopefully those can help you solve all the challenges of steg analysis in the picoGym and other CTFs. So yeah, let's talk about packet analysis now. So what's a packet? Well, a packet is a single unit of network communication. And there's layers to it, and we'll get into that later. And a packet capture is a collection of many packets, thousands or tens of thousands, that's taken from a network interface like your network card in your computer or your Wi-Fi card. And packet analysis usually deals with inspecting and studying that packet capture. So I'm just going to go through these layers really quick. We'll define each more in detail soon. But the OSI model is kind of an academic model of network communication, but it's the standard. It's accepted across the board. So the first layer is physical, and then it's what's called the data link layer, and then the network layer, and the transport, and then the next three are session, presentation, and application. And the model that Wireshark uses is a little bit more simple than the OSI model. It's just physical, data link, network, transport, and then we skip session and presentation and go right to application. So academically, we can think of network communication having 7 layers, but more practically, we think of it having only 5 layers. And that's how Wireshark represents packets. So now, each layer more in detail. So the physical layer this is the raw bits. For wires, it's the electrical current that goes through them. And for wireless mediums, it's the radio signals that transmit bits. Next is the data link layer. And this is connecting to nodes with built-in addresses or hardware addresses. And this layer only deals with the local network. It doesn't try to access the internet at all. And the network layer, this connects with an assigned address, so your network layer address can change. And routing, this is how packets get from one network to another. And this is what lets you talk to the internet. The transport layer, this deals with the multiplexing within the host. So this is going to be a port number, and the port number can be anywhere from 1 to around 65,000. And every port is going to have a different program that's connected to it. And this layer can establish connection reliability if it's using TCP, or not if it's using UDP. And finally, the application layer. So this is structured data for user-facing programs, like for web browsers if you're surfing the internet, torrent programs if you're doing peer-to-peer downloading, or email clients if you happen to be using a non-web browser email client. So now I'm going to show an example packet. So first, I'm going to assume it's Wi-Fi. This is supposed to be radio signals. And those radio signals get converted into bits. And this should look familiar. This is just a hex dump. And we've been looking at this on your computer as files, but it's actually a great way to represent packets as well. Now I'll actually delineate each layer of this hex dump. So the whole thing is the physical layer because the physical signals were converted to bits. But that first line in the hex dump is the data link information. And then we have the network information. Of course, this isn't very readable. Then we have the transport information. And then we have the application information. And this is actually readable because this HTTP request is in plain text. So let's crack open Wireshark and take a look at some packets. So here's Wireshark. I created a packet capture earlier of just random traffic happening on my machine at the time. So here we can see this is the first packet that was captured. And if I scroll all the way down, here's the last packet that was captured. And if you look at this number down here, 5,457 packets are in this capture. And this was a fairly short capture. They can easily be tens of thousands of packets long. So one thing I want to show is sorting. So you can sort based on different fields by clicking on these field names at the top. So if you want to sort by a protocol, you can hit the protocol field name, and now the packets are shuffled in order of protocol from the alphabetical first protocol to the last. And this is ARP. This is a data link layer thing. Let's go to the screen. So this sidebar gives you a higher level view of the packet so you can navigate quicker and more accurately. So let's click on this green part, and you can see it brings me to these green highlighted packets, which are HTTP. So here's the HTTP request. I'm going to close this for now. So here we'll see the layers as Wireshark represents them. So here's the whole packet, or almost the whole packet. You see the frame, or the physical layer part, is the whole thing. Ethernet 2, or the data link part, is the first part of the packet. And the internet protocol or network layer part is the end of the first row and the whole second row. TCP is bigger, and then HTTP is really big, partly because it's not in binary form, it's actually in plain text. But to look at these fields, it's actually a lot easier to do it in this view. You can see the request and the different fields. It has it in a much more readable format. So there are some challenges to packet analysis, such as segmentation. A single communication is broken up into many different packets, and it can be challenging to reassemble those. And just volume. This short packet capture has 5,000 packets, and that's a small one. There's many bigger ones out there. So let's talk about segmentation first. So we can think of segmentation in terms of streams. It's the back and forth between devices. It's a conversation, you could say. And there's a couple tools in Wireshark to facilitate following streams, such as follow TCP stream. And also you can export objects, which is a really powerful tool, which I'll demonstrate. This HTTP communication is actually pretty straightforward. It happens quickly, and the packets are all right next to each other. Or actually, I take that back. They only look like they're next to each other because it's sorted on protocol. If it was sorted on packet number, you can see that these packet numbers are separated by more than just one. But to follow a TCP stream, just right-click on the packet you want to start with, and go down to follow and TCP stream. And so these red highlighted text, this is the client packets, and blue is the server packets. So you can see the request to get the root of the website, and that request is good. And here's the compressed version of the website, which is smaller and easier to transport over the network. And then here we see it's trying to get the favicon, which is the little icon on the tab that's displayed. And it says not found because the website doesn't have one of those. And then you can see this gets automatically put into your filter input box. We'll talk about filters more in the next slide. The other really powerful tool is export objects, and we'll go to HTTP, and it found 2 HTTP objects, the root of that website as one, and the favicon, which is going to be HTTP 404 error. So we'll save this one and check it out. Okay, so here's that file we saved. You can see that it's a just a normal website, pretty plain website, because I have to find HTTP websites to demonstrate because HTTPS is encrypted. So that's not impossible to deal with, but I just wanted to demonstrate something simpler. Finally, volume. Filters are probably our best tool fighting the volume of packet captures. And one of their nice features is that they autocomplete, and they actually do more than that. They actually give you a drop down of all possible autocomplete potentials, and you can select them from that. So it kind of helps educate you on what's possible with filters at the same time of helping you complete them. And a lot of these filters are going to be based on layers. And you can also click on something and apply it as a filter, which can give you hints about how to write filters a little bit more. So for the application layer, HTTP, etc., there's a lot of different application layer filters you can apply. For transport layer, it's mostly going to be TCP or UDP. For network, it's mostly going to be IP. Then for data link, it's mostly going to be Ethernet or ETH. And then if you want any information about the whole frame or the whole packet itself, you can use the frame filter. So instead of using this protocol sorting method, a little bit cleaner and easier way to do this is to type in HTTP to the filter box, press enter, and there it gives you all the HTTP packets in the packet capture. And this number can be useful down here. It's saying that 4 are displayed out of 5,000, and that's a 1/10 of a percent. That can be useful to know how many packets have been filtered out based on your filter. But what I was talking about as far as the autocomplete, if I just type H, it gives me a lot of possibilities. I don't know what a lot of these are. So if you keep typing, just adding a T narrows it down to HTTP. And then if you want a field within HTTP, type dot, and then you'll see all these HTTP options that you can now filter based on. So let's filter based on HTTP responses or response. So this gives us all the HTTP responses, and it returns these simple service discovery protocol packets as well, which is it's just using HTTP under the hood, but these green ones are actual HTTP protocol. You can see that's 13 packets out of 5,000. And then to clear your filter, you can just press this button. One thing you can do, I wanted to demonstrate the applying a filter from the GUI tool. Say you want to look at the packets from a certain IP address. So you right click on this. Notice this IP address is in the hex dump is kind of unrecognizable. It's because it's binary data. It's not plain text. So that's why Wireshark is really powerful in its ability to show you the human readable fields instead of just the hex dump. But if you right click on this, you can do apply as filter, selected. Now that's 30 packets, but every packet is going to come from this 23.202.84.13 address, which can be really helpful when you're narrowing down the packets that you're looking at in an investigation. So that's it for packet analysis right now. There's one topic I want to cover because it comes up in some of the picoGym problems that I'm assigning. So the Caesar cipher. This is a classic cryptography method. It's not secure nowadays because everyone has computers, and computers can go through all the possibilities of the Caesar cipher in approximately half a second. But, you know, like 2,000 years ago, it was a lot more secure. The Caesar cipher is just a shift cipher. And typically the Caesar cipher has the key of 3. And what that means is that the letter is shifted 3 characters down. So A becomes D, B becomes E, C becomes F, and so on. But don't be a hero. Go ahead and use this website to automatically break anything you suspect is a Caesar cipher. And this website works really well. I included this picture. It's supposed to be alphabet soup. So if you see anything that looks like alphabet soup, that's probably a Caesar cipher, at least in these packet captures that I'll be assigning you. So yeah, your picoGym problem set is packets primer, Wireshark, trivial flag transfer protocol, which this one is a stretch challenge. It's there's a lot of steps to it, but it's cool. It's a well-received challenge and it's really good. Good luck.